All right, people are still trickling in, but I'd like to introduce Dr. Sally Dong. Sally did her undergrad in CS and math at University of Waterloo, and she completed her PhD at UW under Yin-Tat Lee and Thomas Rothfuss. She was also an applied scientist intern at Amazon in Luxembourg, and word I got is that they were interested in hiring her, but she ended up doing a postdoc now at MIT's Sloan School of Business, which has a long tradition of excellence in optimization. And I understand she's now focusing on problems in social science and operations management. But today she's going to tell us about some of her PhD work, which I was particularly interested in seeing. I think this is really insightful work and potentially practical. So thank you for coming, Sally.
Thank you so much for the kind words, Phil, and thanks to everyone for coming to this talk. So today I'll be talking about basically my entire line of PhD work, which kind of builds on top of each other in a really nice way, I think. And the focus is on solving linear programs faster. So without further ado, let's get started. Just so we're all on the same page, let's start off with a reminder of what linear programs are, right? So we're given here some linear function we're trying to minimize over multivariable x. And we have constraints that are also linear in terms of x. And we also have some non-negativity constraints. This is the most general form for a linear program. And for today's setting, I'm going to say that instead of the traditional m by n constraint matrix, we'll say n by m, because then this maps very naturally onto flow problems where the variables are on edges, which tend to be denoted by m. Okay, so linear programs are very general, and there are a lot of general linear program solvers. And people have been working on this for 50 years. It has lots of applications and everything. But for this line of work, we are particularly interested in linear programs with some structure in the constraint matrix. So one very simple example is the following. All right, so we have this constraint matrix, which we can see that it has a block structure, meaning that there are two blocks in the diagonals, and the first block has nothing to do with the second block, right? So if you want to solve this program, you can think of solving the first one independently of the second block, right? So you solve for x1 and x2 based on the first constraint, and then you solve for the other three variables. And basically, we've broken down this problem on 5 variables into a problem on 2 and 3 variables. And you can think, if our runtime is not linear, then it's faster to do it by using this breakdown. Okay, and this is just a very simple example for structure. And now what if we have something more complicated? Okay, there we go. Okay, so some more examples for constraint matrices. So on the right-hand side, it's a very general constraint matrix. And on the left-hand side is something that looks like it has more structure, right? Like the non-zero entries form this nice zigzag. And intuitively, we think, okay, the left one should be easier than the right one because there's fewer interactions between the constraints and fewer interactions between the variables. And how do we formalize this measure of interactions between the variables and the constraints? So what we'll do is define a graph that represents the constraint matrix. And the process goes as follows. So the rows are going to represent vertices in a graph. So here we have 4 rows, so we have a graph on 4 variables. And then for every column of this constraint matrix, we're going to associate that with a clique. Okay, so here, if we look at the first column, it has a non-zero entry in the first row, and that's it, right? So we put a little self loop here on the first vertex. And then for the second column, we have two non-zero entries on the vertices 1 and 2. So then we put an edge connecting the corresponding vertices in the graph. Okay, and then in the most general case, if we look on the right, if we look at the first column, it has all non-zero entries. So we put a clique on the 4 vertices, 1, 2, 3, 4. And basically here we've got a multigraph because every column gives you a clique on these 4 vertices. Okay, so I hope that's clear how we get this graph. And if we call the constraint matrix A, then we call the graph like G of A. And now we can think about structures in this graph. And then we have kind of very traditional graph theoretic notions like what does it mean for a graph to be planar, low tree width, separable, all of that. So yeah.
Do you have any intuition why like I would add a self loop in the case where I have a variable that participates in just one constraint, but like if I have a variable that participates in 2 or more, I'd add a clique but without self loops? Like,
Actually the self loop doesn't matter. I think it's just for definition purposes. We say like, yeah, there's an edge. There's a clique on a single vertex. So whether you add the loop or not, I guess it doesn't matter. Yeah. Right. So we're talking about structures and graphs, and so here are some examples. We have planar graphs, which are known to have the number of edges on the same order as the number of vertices, right? And in the case of non-planar, the number of edges can be up to quadratic in terms of the number of vertices. And then one other traditionally studied notion in graphs is low tree width, which intuitively means that the graph looks like a tree. So, we have some extreme examples of low tree width versus high tree width. And they also have this property that the number of edges is bounded in terms of the tree width and the number of vertices. Okay. So yeah, what about like in practice? Do these structures actually show up? And it turns out they do. So road networks, we all know like they're planar because whenever 2 roads intersect, unless you've got a bridge, they have to cross, and when they cross, that's a vertex. So empirically, people have shown that they have good separators. So this is actually a bit stronger than planar, but we can think of road networks as planar. And then in terms of tree width, so when we wrote this tree width paper, we actually looked at a bunch of linear programs in this MATLAB library, and we plotted the tree width of those linear programs versus the number of variables in those linear programs. And then we saw that there was this correlation between the 2 variables. So in general, we saw a lot of sublinear tree width for these problems. So that's to say, if we can solve these problems faster when we do parameterize by these structured parameters, then we actually do better on a lot of these practical problems. Okay, so I'll just get into our results. Linear programs have been a huge topic over the last 10, 15 years. So I'll skip over most of the literature review and only tell you about what exists compared to the best I'll only tell you about the best existing work compared to our results. So the first result we had was solving linear programs for these low tree width matrices. And in that case, we have the runtime m times t squared, where t is the tree width of the constraint matrix. And the previous best was this m to the 2.37, which is the matrix multiplication time. And that was for basically all general linear programs. So if you imagine if the tree width is low, so if tree width is, say, square root of m, then we get something that's better than the existing best runtime. Okay. And then the next work that we had was for solving separable linear programs, which I didn't really define, but this is another notion that connects very closely with low tree width and planar. And in this case, we also have a runtime that improves over the best, which is just a general linear program solver. Okay, and sorry, okay. And the thing to notice here is that if it is separable with this alpha parameter being less than 1/4, then this is a nearly linear time algorithm. Okay. Yeah.
Is alpha just the exponent size balance separator? Or
Yeah. Yeah. Okay, so those were the results for general linear program solvers when we have some sort of structure. And now we come to this class of problems, which is min-cost flow. And here, okay, so the problem is you're given a graph with n vertices and m edges. And at every vertex, you have some flow demand. And your goal is to find a flow that routes the correct demand. Right, and everyone learns about this problem in Algorithms 101. And this problem, you can solve it using, for example, Ford-Fulkerson, but you can also write it as, well, okay, sorry. Max flow is Ford-Fulkerson, but there's something similar for min-cost flow. And instead of doing that, you can also write it as a linear program, right? And then we can apply our linear program solver to solve this problem. And when we write it as a linear program, so we see something interesting. So this constraint matrix actually exactly encodes the graph, which means that when we construct our graph, like the way I talked about earlier, the graph we get in response is actually the original graph given as input to the problem. Okay, so then when we talk about solving min-cost flow on planar graphs, the corresponding matrix also has this planar property. Okay, and then for min-cost flow, we have the following results. So for planar graphs, we can do this in nearly linear time. And this was an improvement from the previous best, which is n to the 1.5, which is a big result back in 2008. This is Deitch and Spielman. And then later for min-cost flow, we know there was this big line of work, big paper from these folks. I'll not name all the authors, but basically they solved the problem essentially, and they got this almost linear time algorithm for all possible min-cost flow. So general min-cost flow, not just on planar graphs. But actually ours on planar graph is still a little bit better than theirs because they have this little of one term in the runtime, and for us, we are almost linear. Sorry, we're nearly linear, which is better than almost linear. And then, yeah. And then just as a small follow-up, we also extend this min-cost flow on planar graphs to min-cost flow on low tree width graphs. And essentially, this is using exactly the same tools. Just instead of planar, we use this other tree width parameter. Yeah.
Maybe a silly question. Yeah, we get the goal, which says that think about the graph corresponding to constraints, and that's planar. I guess I could solve it in linear time. Should it be clear to me that if I give you a planar graph and I think about the constraints for min-cost flow, that the graph corresponding to the constraints of that LP is also planar? Or is that's not how I get the
So we defined the graph corresponding to the constraint matrix so that if it is a mean cost flow problem, the two graphs are exactly the same.
Oh.
Yeah.
Oh, I guess that makes sense.
So if you imagine, so this is the mean cost flow constraint matrix, right? This B transpose, which is essentially, so it's got vertices of the original input graph as rows and edges as columns. So for every edge, you have so every column is an edge, so there's two non-zero entries, which means you put an edge between the corresponding vertices of the graph. Yeah. But there were other ways of defining a graph corresponding to a constraint matrix, and this was used for other papers looking at solving integer programs with low tree width, but we didn't go with their definition precisely because we wanted our definition to match with the mean cost flow graph. Yeah, and then one comment on this mean cost flow on low tree width graph is for a general graph, the tree width is just n. Then we get the runtime, which is m square root n, which means we are matching this old result by now, the Lee Sidford result of 2014. So that one, they had this big breakthrough where they showed they could solve general mean cost flow in m square root n time, but they were using a very fancy IPM technique. And essentially, we're only using
Carrier point method.
Sorry. Oh yeah, very fancy convex optimization technique, and we showed that we didn't need their fancy machinery in order to get the same runtime.
Sorry, but that paper is for general.
Yeah, right. So as a corollary of this is we have that for general graphs, we can solve mean cost flow in m square root n time, right? So that matches the Lee Sidford result. Okay, and then finally, this comes out also as a corollary of the general LP, of our structured LP solver, which is we can also solve K commodity flow on planar graphs in an improved runtime. And K commodity flow is essentially mean cost flow, but instead of just having one type of demand, you could have K types of demand at every vertex, and every type of demand has to be fulfilled by the flow. Yeah.
Sorry. Is there any result for planar graphs that beats K times n?
For
mean cost flow commodity flow.
How would you write down the output?
You can. So you can do constant approximate commodity flow and for m plus k to an exponent you would implicitly represent the output. But I guess I'm wondering if some way for planar, maybe get rid of the approximation factor or something.
Oh, interesting. We should talk offline.
Yeah.
Yeah. And I guess to compare to existing work, again, there was no work kind of like looking at this is high accuracy K commodity flow. So basically, we're only comparing against the general purpose linear program solver with this like n to the 2.7 exponent. But afterwards, or like around the same time, this is Jan van den Brand, they also worked on K commodity flow for general graphs, and they have this runtime, which is good, but for planar graphs specifically, we do better than their runtime. Okay, then let's get into talking about some of the ideas. And there's a lot going on, so I'm just going to kind of give a very high-level overview of key ideas and intuitions, And a lot of details are very fuzzy and not very accurate, so be warned. Okay, so we'll start off with interior point methods, which is kind of the backbone of all of these recent fast linear program solvers. And here's the idea, right? So we have our linear program, and we know that this corresponds to optimization over a polytope. So every facet of this polytope corresponds to one constraint in this constraint matrix. And this C, our objective function, tells us the direction we want to optimize. Right, so we know that this corner, which is the most you can go in the direction of minus C, is going to be the optimal solution. And in interior point methods, we start off by defining something called the central path, which is this white dashed line. And the idea is that we want to start off with some point in the interior of the polytope and try to follow this dashed line from the interior to that optimal point. And this dashed line, the central path, it's parameterized by this parameter t, that as we move t down from infinity to 0, we get closer and closer to the optimal point. And with interior point methods, this is going to be iterative. So we start off with some point, we start off somewhere in the middle. We try to follow this path. We take 1 step, 2 steps, and slowly, basically, we converge to the corner. But we never get to the corner, right? We round off at some point. Okay, so if we think closely about what happens at each point, so at a step k, let's think of what's happening. So we have our solution, which is a tentative solution to our linear program. So it's not optimal yet. So we call this xk. And then we want to compute a step moving us from xk to something a bit better. So that's, we're hopefully decreasing the objective value. Right, and the goal is to move closer to a point on the central path where the point on the central path is slowly moving towards the optimal point. And just like some quick observations, we know at every point we start with x0, for example, and x1. And since we're always inside this polytope, it's always going to be a feasible solution, right? So then we can see that the step we're taking, has to be in the kernel of A. Just basic observations about what's going on. And if we think about the flow setting, we're updating a flow each time, right? So our tentative solution is a feasible flow, and we have to update to another feasible flow, which means that the update has to be a circulation. Okay, I see Phil writing things down, so I'll take a pause.
I've seen this stuff before, but
Okay, right. And I haven't gotten into the details, but just from the very basic explanation, we see that in order to compute the step, which is a length m vector, just very naively, you need to take O of m time, right? Because you have to read every entry of this vector. And just from basic interior point method theorems, which have been established for a long time, square root m steps are needed. And if each step takes O of m time, then already that's m to the 1.5 time. And earlier I said we have results showing that you can do this in nearly linear time. So this is already not good enough. Right? And actually, so this idea is already exactly how Daichi-Spielmann got their planar min-cost flow results. Okay, so then our task is to speed up each step here. And okay, this is the most math there will be. So let's think about what exactly each step is. And without getting into too much detail, essentially what we're doing is we're trying to find an optimal step with respect to the central path. So this delta mu, the idea is that you're moving closer to the central path, right? And moving in that direction is not necessarily feasible. So there's some projections so that we know that the resulting step is a feasible step. Okay, and the key thing to notice is that when we're looking for this step, this delta mu is going to be a function of my current position, so where I currently am with xk, and w here is also a function of the current location xk. And here, so I'm just rewriting this large expression as something that's kind of like a projection of the direction that we want to go. Okay. Okay, so that's the classic interior point method. So now let's get into the robust interior point method. So in the classic version, right, we always have x0, x1, x2, xk at every step. And here we're going to say, okay, xk exists somewhere in a data structure, but we don't know exactly what it is. But instead, we'll keep an approximation x bar. And the idea is that this x bar is going to be a coordinate-wise approximation of the true current solution. And at the very start of the algorithm, we just set the approximation to be the exact solution. Okay, and let's think about what happens from the point x1. So from x0 to x1, imagine we already took this step, and now we have x1, which is hidden in the data structure, and then we have x1 bar, which we can access. Right, so at this point, we want to compute some Newton step delta from x1. But okay, we don't want to do this because this is going to take too much time. So instead, what we're going to do instead is compute a kind of a different Newton step so this Newton step is going to be like, taking gradients and Hessians at this point x1. So instead of taking gradients at x1, we'll take the gradients at x bar, right? And then when we do this projection, it's also we're going to do this computation with respect to x bar.
What is V?
It's just I just rewrote this to be V. So that's the direction according to optimizing with respect to the central path. Yeah. Yeah, right. Okay, so instead of taking gradients and Hessians at x1, we're going to say, okay, we'll do this at this approximation. And because this is an approximation, we should still go in the correct direction in terms of the overall optimization goal. But still, this is not possible because we don't want to compute even this delta at x bar. But we know what it is, right? So we can write down the symbolic expression for this step. And what we'll say is, we'll tell this data structure, okay, we want to move in this direction, and we know the symbolic expression of it, but we don't want to actually evaluate each point in this vector. And our data structure is somehow magically going to tell us, okay, like we know that you want to go in this direction. I'm not going to compute exactly what it is, but I will tell you exactly what x bar is at the next step. So the data structure internally is updating x1 to x2 according to this direction we want to go, and then giving an explicit approximation in return. Okay, and then we repeat this over k steps, over square root m total steps, and then at the very end, we don't want this approximation. We actually want the exact solution. But we only ask for it once at the very end, which means that we can spend more time on it, right? We don't have to do this O of m square root m times. Okay, so exactly what's going on with this data structure, let's summarize a little bit, right? So first we want to take this Newton step, which involves computing Hessians and gradients at x bar. And luckily, we know that the step direction is going to be a function of x bar entry-wise. So if x bar, let me get back to this. Okay, so we just know that this direction is a function of x bar entry-wise. And as promised by the IPM, we also know that the change in x every step is bounded in to norm approximately. Okay, and then finally, we have this guarantee that between x bar at k plus 1 and x bar at k, they only actually differ on a few entries. Okay, a little magical. And what exactly is it? Well, so x bar at k plus 1 is going to be very explicitly the following. So if the real x changed a lot within the step, then we'll update x bar to match the real x. And if it didn't change a lot, then we'll just keep it at the existing value. So, you know, if x bar at k was a good approximation to x at k, then this definitionally means that x bar at k plus 1 is still a good approximation, right? And okay, so I lied a little bit here. The data structure doesn't return the full x bar vector. It only returns the coordinates that were changed. And that means you're not operating on a length m vector. You're only operating on the coordinates that changed. And now, given the changes here, in the next step, when we're computing the Newton step, right, we're giving the changes instead of giving it the full x bar. And then to compute v at the next step, we only need to compute it with respect to the changed coordinates. So because we're only looking at changes at every step, and we have this magical property that the change in true norm is bounded, we can bound the total number of coordinates that we're working with. Okay.
What's the stopping criteria for the number of steps?
So this is guaranteed by the interior point method. And essentially it's saying after square root m iterations, we're guaranteed that our solution is within epsilon of the true optimal solution. Yeah.
Yeah, so it's not,
So it's not adaptive.
Right, right.
It's not, and it's not really a fundamental change in the interior point method more generally. I think it's just how it gets implemented and what approximations are taken along the way.
Right.
Is that accurate?
Right.
So we can, so you can just use the bounds on the interior point, on the interior point method as previously known.
Yeah, essentially. And then this robust interior point method is basically showing that, you know, instead of computing the Hessians and gradients at the exact x, we can do it at an approximation, and it still gives a good direction for getting closer to the optimal.
So is that what robust means in this context? It means you can tolerate an approximation and
Yes.
still make progress.
Yes, exactly. Okay, right. So to summarize, this is going to be kind of abstractly what our data structure does at every step, right? So as input at step k, we're given the updated entries of x bar. And then the data structure will compute the new entries of v, which is the direction we're moving towards. And this v is going to involve gradients and Hessians of evaluated at X bar. And then remember, we also have this projection matrix, which is also a function of X bar. And the data structure will implicitly update our solution X by the step we want to take, but somehow, right? Somehow. And then after the data structure has done this, the update, we'll get the entries of the updated X that has changed a lot corresponding to the previous step. And for those entries, we have to get their exact values. And then we put those exact values as the X bar. And then the output is going to be these updated entries of X bar. Okay. Yeah. Good, good. So hopefully that's somewhat clear. Okay, so then let's get back to exactly what this step is that we're taking. All right, so remember this expression, the step is some projection matrix applied to some vector. And now, so suppose for an example, the graph of the matrix is this little planar graph that I've drawn. Then if we look at this projection matrix, it's basically entirely a function of this graph structure, plus the fact that these W's are changing. So W's should be interpreted as weights on the edges of the graph, okay? And the weights are a function of X bar. So remember, so X is supported on the edges, so X bar is supported on the edges, so correspondingly the weights are on the edges. And so we'll just say that, let's call this matrix, this big expression, M, and it's a function of our graph. When X bar changes, and the weights,
and the weights change every iteration.
Exactly.
As well, right?
Exactly. Okay. And here's a little aside. For flow problems, we have kind of a nice interpretation of what exactly this means. So if we break down this big projection expression, then this first term, so from A up to the end, that's actually giving you some demand on the vertices, right? And then when we apply this inverse, this is turning demands at vertices into electrical potential. So this is relating to electrical flows, right? So after you turn it into potentials, you hit it with A transpose and W on the other side, and you get an electrical flow, which is a flow. And essentially the idea is every step in a flow problem, we're updating a feasible flow with some other circulation and then getting a new feasible flow. So the update is an electrical flow that represents a circulation.
Now, is this interpretation valid even for multi-commodity flow?
No.
So just for single commodity flow?
Yeah. Mm-hmm.
Is there something analogous, perhaps, for multi-commodity?
That's a good question. I haven't thought about it. Yeah, maybe we could talk offline. Yeah, because for multi-commodity flow, we're not using the flow interpretation at all. We're just looking at it as a linear program. Yeah. Mm-hmm. Okay, so that's kind of the interpretation as an aside. So let's get back to kind of understanding what exactly this matrix is as a function of the graph and the weights. Right, so using the same graph as an example, let's talk about what it means for a graph to be separable, which is the property that we'll use to make all of our data structures faster. So here's our graph, and here's this concept of a balanced separator, which is a set of vertices whose removal will split your graph into two approximately equal halves. Yeah, period. Okay, so if we find a balanced separator and we separate this graph into two halves, then we could recursively apply this separation procedure. And so we find another separator and so on and so forth. And this gives us a tree in the end, right? Where the tree just encodes exactly how we decompose this graph. So just to clarify, this piece went here and the bottom went here, right? And same thing on the other side. And because we are always separating one subgraph into two approximately equal halves, the height is going to be on the order of log. And at the very end, we stop when the leaf nodes are constant size. Okay, so now back to our step, right? So we said it was some matrix applied to a vector, and the matrix is a function of the graph. So now we can think of this matrix as being something that was on a graph, but since the graph can be represented as a separator tree, this is something on a separator tree. And exactly what it is a little complicated, but if you recall, like there's the expression for the matrix, and we're just factoring this middle expression into two parts. And the idea is it corresponds to traversing up and down the tree. And so let's think of what happens when we apply this matrix to exactly just one coordinate of v, right? So applying a function to, say, just the basis vector in direction I, what we're going to do is, okay, we look for this vector, this entry I, which corresponds to an edge. We look for that edge in the separator tree, so it's here. Then we're going to do something with respect to this edge in this tree, and that's going to be the output. And we do this for every entry of V. And the punchline is traversing up the tree is efficient and down is not. So this will be lazily processed. And again, it's better to illustrate exactly what's happening with the flow problem because it has a very natural interpretation. So consider this flow problem setting again. So we're trying to compute the step in x, delta x, and we're just looking at one entry of it. So it's matrix applied to the direction vector taken at one entry. So we're looking at entry I, which corresponds to this, this edge I here, right? And we think of it as connecting. So if this is some value, let's say A, then one side is we're going to imagine we're connecting some external wires to the two ends of that edge, and it's giving some current in and then some current out, with current in and out both being value A. So basically, we're translating this edge value to vertex values, and this corresponds to doing a small bit of the computation. Okay, so we're talking about electrical flows, right? And now we have some demand, which, you know, it's the same thing as net current. Okay, so then we can talk about electrical potential. So we have, this is an electrical circuit. We know we have some current coming in here, some current going out. That means there's electrical potential at every node within this region. Then we can compute those potential. We can also compute the demand, which is the same thing as current, on the boundary. Because essentially what we're saying is we have this overall electrical circuit and we're focused on something like the current flowing within this. But when you put currents in and out at these two nodes, electricity flows across the entire circuit, right? So right now we're only focused on this one small part, which means that we can compute these potential, and at these nodes, we know that current is flowing out towards the rest of the graph. So we're, yeah.
Is it something like shear confidence going on?
Yeah, yeah.
Are that taken care of? Like how much flow is on the boundary depends on the outside graph.
Yeah, right.
What you're describing seems very local to this leaf node.
Yeah, it's exactly short complement. And basically, we're computing what's happening at this leaf node, and then the rest is happening like further up in the graph, sorry, in the tree.
So following up on that, what you're saying is that your complement enables you to sort of summarize the rest of the network?
Yeah, exactly. Right, right.
I guess all that happened while you were constructing this tree. You just
So we construct a tree, and then at every step, this is happening over and over. This is happening at every step. Yeah.
But the point is, this leaf node knows the shared complement. Like it has the.
So the short complements are also changing because the weights are changing. Yeah. So at every step, all the short complements are being recomputed, but it is the same non-zero structure. Yeah. Right. So the goal overall is to compute the electrical flow, like in this overall circuit, right? And now we figured out something's happening in the small piece, and we have to understand, okay, after these currents come in at these two nodes, what happens to the rest of the graph? And by traversing up the separator tree, this is kind of saying, okay, we know what the demands here are, which is going to help us with figuring out what's happening outside this piece. So we're passing the demand to the parent node, which then lives on kind of the boundary of the child node, right? And from these demands, we can compute what the currents are, what the voltages are in exactly these two vertices. And then you repeat this process until you get to the root. And at this point, we basically have information at these interior vertices, which they're called eliminated vertices, but long story. But essentially, these sets are disjoint, right? And at every node, we have some voltages. It's not real voltages, but it is a summary of voltage information. And after we get to the root, this is equivalent to having done this part of the computation, which is half of m times vi. And then for the other half, we're, instead of moving up the separator tree, we're coming down the separator tree. So starting from information at these nodes, we're going to look at the root node, and basically push whatever information was, on the separator set to the two children. And this also involves the transpose of these short complements, essentially. And then we repeat this process, and we send more information to its children, and until we get to the very end, so this entire process across the whole tree, that corresponds to doing this full computation. And after this, we have the true voltages at each region. And this is after a global computation. And then with the voltages, we can convert to flow, which corresponds to multiplying by W half A transpose. And then we combine all the flows on each region together to get the overall flow, which is the answer to m times vi.
Is it literally true that you're doing these computations independently for each entry I?
No, and I'm going to get to that next slide.
Okay.
Right. So this is for one entry I, right? So what we're doing is we're going up one path of the tree and coming down all the possible paths. I'll get to that in just a second. Yeah. Right. And okay, well, so up is easy because we only have to traverse just that one path up the tree, which is log n time. But coming down is hard because we have to traverse each node. And how easy is up? Well, so for one entry, the time is going to be square root n to traverse up because at each level, we're only focused on the separator, which is square root n sized. But if we have r different entries, then we do this in parallel, right? So we compute everything at the child level, at the leaf node level first, and then we move up everyone together. And if you do this, then we just bound the sum of the separator sizes. And it turns out you don't have to have this r times square root n. You get square root of rn. So we get a saving of square root r. Okay. And okay, so up is easy, and that's solved. And what about coming down? So we don't want to traverse the whole tree at every step. So let's just go up and then leave it as is, right? So we have some information at each node. Essentially, this corresponds to the separator at the node, right? So these are the separators, and across the whole tree, these sets are disjoint. So we'll just always store these information in our data structure. And we don't ever traverse down unless it's necessary. And when is it necessary? One, when the weights change. And two, when we need to get the exact entry values for figuring out which entries changed a lot. But it's a lot of detail, so I will leave it at that. And essentially, this is the full idea. So taking advantage of the separator tree, doing lazy computation, and then there's a lot of finicky details to work out. But that's all for me today. And this work was done with a large group of collaborators. And thank you for your attention.
Questions? More questions?
Yeah.
So I have a naive question about your initial formulation.
Mm-hmm.
I remember from linear programming that for different circumstances, there's all sorts of tricks for basically changing the constraints by introducing variables or new constraints.
Yeah. Mm-hmm.
So suppose I start with a formulation, a matrix, and its tree width is 10.
Mm-hmm.
Can there be some way to rewrite the linear program to get an equivalent linear program so that in your framework, the tree width of the new linear program is 9 instead of 10?
That's an interesting question.
Therefore,
Mm-hmm.
it becomes faster in your framework.
Right. I don't think so. And as part of that first tree width result, we did think about rewriting the linear program. So for example, for any linear program you give me, I can rewrite it so that each constraint only involves 3 variables. But the way that we could do it was so that like the tree width stays the same. So like we could not think of ways to reduce the tree width, so to speak. So
but could not think of is not
right, exactly.
Prove
yes.
An inherent characteristic of a linear program.
That seems too much to hope for. In fact, I think going from the tree width to small separators, you're already paying a constant factor there. You're paying like a factor of 2 or something of the size of the, I think, going.
Oh, you mean like
the sizes of the separators for the decomposition tree.
Right. Mm-hmm.
Slightly bigger than
the
tree width.
Yeah.
Balanced.
Right. So for constructing the separator tree, tree width is a weaker concept compared to small separators, because small separators means recursively smaller, whereas tree width means constant recursively. And that's where the difference in the runtime comes from.
Your questions?
So in the new generation of directed max flow algorithm, they solve, instead of square root of m, they solve a linear number of
Yeah.
like
Mhm.
dynamic Goldberg and that.
Right.
Like, can you say something about the connection?
Uh,
Because I think that what they do there is they also only update the gradient. So the way I understand that algorithm, so I would try to run some kind of gradient descent, but I only update the gradient on the edge if the gradient has changed a lot.
right,
Which
right.
resemble some of the things too.
Yeah. Yeah, but I still think fundamentally, if you're using so they're using a fundamentally different interior point method is how I would say it. And they're still designing like very efficient data structures for their interior point method, but like some of the approaches within the interior point method is different. So yeah, so I guess the overarching theme for all of this work is you have interior point method and then you have fast data structures to support the interior point method.
Yeah, so I think for those interior point methods, the number of iterations is linear. But
Yeah,
but you're just managing to do each iteration very fast.
Right.
They're doing L1 ball
Yeah.
stuff, which is not what this is.
Yeah, this is L2. Yeah.
I just want to make a comment. To me, so going long back, when separators were first found for planar graphs, there was this notion of generalized nested dissection, which generalized something that numerical people had already been noticing, that very often they, in order to solve linear systems, which comes up a lot in numerical, in solving, say, numerically solving partial differential equations, you're using the separator structure of the graph, and they got it faster. And that was a really big deal, just for solving linear systems. And what Sally and her co-authors are doing is solving a much harder problem of linear programming. And so, but this is an analog of generalized nested dissection for linear programming. So I think this work is going to have, you know, is going to really be important as practitioners.
You're more optimistic than I am.
Yeah. Well, maybe because I know few of the details. All right, no further questions? Thanks for